you by now. I'm Shreyasha. I'm a researcher at NAAMII, and at NAAMII, I've mostly been looking at AI and society. I hope it's not too much today because we're going to talk more about bias. But since the previous lectures have covered it a lot, I'm hoping you guys can help me do some of the talking, and I'll put some slides, I'll ask the questions, and please join along with me. I've also gotten feedback that the lunch session is the hardest to be aware, so we're going to make this more interactive, and hopefully none of you will fall asleep. So let's get started. I have an icebreaker. We've used Slido before. How many of you remember it? Yes, so let me switch my screen. And then, yeah, so, nope. Let's go. Yeah, the code is over there. Can you see the code on screen? If not, can our volunteers put it on Zoom chat? Better? No. Okay, can you see the code? This is getting a little difficult. Okay, discrimination, racist, basic framework of AI. Anything else? We had 2 talks. Come on. China. Anything else? Black and white, uninclusive data set, human nature. I'm gonna blocklist names. So this time we have a speaker who understands Nepali. So let's not do that. That's probably not AI. This is also probably not AI. Okay, too many names. I'm gonna assume you guys are bored. Yes, so let's get to the slides and oopsie. Okay, perfect. So what we're gonna do, and because you guys put a lot of names, a lot of my myths didn't show up, but some of them we did hear in our talks earlier as well, right? There's lots of myths about machine learning, bias, and what I hope to do in this talk is not give answers, because there's not a lot of answers, but try and connect some of these ideas that we heard in the morning with some of the maths and algorithms we've been learning the past few days, right? So that next time you guys build your own model, you can think about where bias can seep in, what we can do about it, whether it's good, whether it's bad, right? As engineers, should we think about bias besides like the impact on society? So myth 1, we hear this a lot. We've been hearing this since almost middle school when we hear about garbage in, garbage out, right? Bias in machine learning is a data set problem. If you give bad data, you get bad results. And so a lot of bias seeps in because of data. partially true, but not complete. And we'll see how and why and where exactly in the machine learning life cycle does bias seep in later in the talk. Myth number 2, algorithms do not create biases, they transmit biases. Again, if you remember talks in the morning, a lot of people talked about historical bias, systemic bias, structural bias, right? And the examples they were giving was biases that already exist in society that then were propagated or transmitted by the algorithm. Again, partially true, algorithms do transmit biases, but sometimes they also create biases. It again depends on how we design the algorithm, and a lot of choices we as engineers choose while choosing optimization methods, right? We learned about different optimization techniques earlier. Metrics, whether we choose to highlight accuracy, true positives, false positives, true negatives, and we'll go into it little bit later. Myth number 3, biases can be fixed to make the algorithm more fair. And a lot of time I'm going to spend today, and I hope it won't be too confusing, is this idea behind fixing of biases and fair algorithms. Fairness by itself is an area of active research. There's lots of really smart people in really famous universities working, trying to define a fair algorithm, and it turns out it's not that simple. Surprise. And then myth number 4, this I haven't heard as much nowadays, but I think people still think about it where let's create something first and then we'll test it, we'll evaluate it, we'll make it fairer, we'll make it less biased. So we think about algorithm design as the first step and then making it work well as the second step. But as we'll see, sometimes they go hand in hand. Iterative processes, right? Bias and fairness can seep in at every stage of the life cycle. So we do have to be aware of it at each step of the algorithm design. So now that we've learned some of the myths, let's go into some math, right? So sources of algorithm bias, it's not only a data problem. So has anybody seen this diagram before? In the audience, on Zoom? I can see raised hands, I think so. If somebody has, you can raise your hand. Nobody? Yeah, so this is from this paper that I've listed in the little rectangle below. And I really like this because the paper is about unintended consequences of machine learning, but it spends a lot of time thinking about bias. And this is basically the top, right? Part A is where we create data generation. And so this is different biases that seep into the data. And then the bottom part is model building and deployment and different sources of bias that come during those processes. Nope. Yeah, so going back into our data set bias, the boxed area is where bias seeps in from the data. And if we go mathematically, these biases are named as historical bias, representation bias, and measurement bias. But there are 3 other kinds of bias that come during model building and evaluation. One of them is called evaluation bias, which is the biases we introduce during evaluation itself. And then the last one is perhaps the most important, which is the deployment bias, which is the bias that exists when we develop model in our labs, in our projects, in our research, in our companies, and then put it out in the world. And then surprise, the world is more complicated than we imagine it to be. And so there's always a bias that seeps in when we try to model this complicated humans and multiple interactions and multiple agents, and then try to build a model. Yeah, so I do have slides about each of the biases, but I think we've gone through some of them earlier in the morning as well. So we're gonna go slightly faster. So the first one is historical bias. Here's two real world examples of biases that we saw in AI algorithms that were actually being used in real systems. That were actually being used in real systems and had real impacts. The first one was University of Texas used an algorithm to evaluate computer science PhD applicants. A lot of you I know are thinking about applying to PhDs, so it's directly applicable. And what happened was historically UT PhD students were white and from certain parts of the US, and then the algorithm learned to favor those compared to more diverse applicants. So female students, older students, right? Poorer students, non-white students were actually rejected before even a single human looked at the application. And they had to end the use of algorithm. The second one was hiring algorithm. Again, we heard a little bit about it this morning. This is Amazon, not IBM, but Amazon had an AI recruiting tool. And again, because most employees of Amazon were men, and statistically they were more likely to be promoted, the AI algorithm ended up only recruiting men because again, the algorithm was tuned for more higher true positives and it showed bias against women. In both of these cases, gender was not used as a feature, but because historically, systematically, gender, race, poverty have been used to cause like lack of opportunities, right? When we think of opportunities or people with merit, we kind of end up using those as proxies. Yeah, so historical bias, this is just a definition where even if our data is perfectly measured and sampled, because historically the world itself is biased, our outcomes are biased. Representation bias, which one is a better classifier? Is it the red line or the blue line? We've seen these classifiers, I think in the first or the second day. I hope we remember this. Which one is a better classifier? Red line. We can say that from the right-hand side image, but can we say that from the left-hand side image? No, for the left one, both models are equally good, but there was some hidden data we didn't see on the left one, which we saw on the right-hand side image. And so now we are like, okay, red one is better. So representation bias occurs when certain parts of the input space are underrepresented, right? In this case, this black, can you see my cursor? Yes. This black dots and these blue dots didn't exist here, so we had no way of evaluating which classifier is better. Once we saw those data, we have a much better understanding. And this is sort of how it exists in real world when some demographic characteristics, when we don't think about it, we end up creating a model which we think is good, but may not be when we have information about all the features or all the data points in the world. So again, practically, how does representation bias occurs? One is what we call sampling bias. Often data sets are biased by where the data collectors opt in data from. You guys have done a lot of machine learning projects now, right? How do you get data? Most of the time we Google, we find open source data sets, we use them. We have no idea where the data came from. Many of those data sets are crowdsourced. So most of the time that data is provided by somebody at least who has access to internet. We also know many people who don't have access to internet, right? So that's one bias. Second bias, access is one of them. Again, annotations, right? A lot of these data sets are annotated in a crowdsourced manner. So we don't know how the annotators are given instructions, how like you distinguish between a table and a chair and a bench, right? And so if we dig into the data sets, often like data sets that are annotated in the United States versus China have their own sets of cultural biases. Often data sets that come from developed parts of the world. I used to work in self-driving cars. So a lot of the data sets that I used to work with had nice lanes, lane markings, dividers, right? pedestrian walkways, and then I come here, walk along the roads of Nepal, and none of them exist. So the algorithms I developed are biased and have sampling bias in terms of the quality of road. Even now, if you've done any project related to cars or driving, like the data sets that you see are very different to data sets that you would collect if you went out on the road and collected. The second one is missing context, which is data set collected in one context for some specific purpose is used for a different purpose. We see this a lot in social science related data sets or language related data sets where we use Wikipedia data set to build semantic models or semantic labeling or sentiment analysis, or we use Reddit data to do sentiment analysis. And I'm sure like the language you use for communicating with friends on Facebook Messenger versus Reddit versus Google is very different. At least for me it is, and I'm sure it's the same for all of you. So we can almost imagine the bias that seeps in, right? If you use Reddit data set to model language we use for communication, and then use it to analyze, say, Kantipurko media results. There's a bias, they don't work, they are completely different contexts. So this is again representation bias, where data can be collected in different contexts, and oftentimes that data set is very dependent on the context, because language is easy to think about. Again, roads, like going back to self-driving cars. Collecting data set for a sunny day is very different from collecting data set on a rainy day, because now you have to consider lighting. Collecting data set for driving in the United States is very different from collecting data set for driving in Nepal, because the traffic rule is different. You'll have a lot more motorcycles, you'll have a lot more pedestrians. Sometimes you'll have cows and dogs in Nepal, which you won't see in the US. So if you use data set trained in with data set from the US, it won't work here. And that's because some parts of the driving context is not represented. And that's a representation bias. Here's some real world example again. For COVID, people tried to create a lot of contact tracing apps, some of them automated. And what happened was, again, this is from the US, right? We collected mobility data using your location, your smartphone data, your Bluetooth, and then learned that a lot of older people, a lot of poorer people don't use smartphones. No smart tracking, no location, sometimes not even Bluetooth. So people who are actually more at risk, people who might be traveling a lot, were actually completely removed from the data set and the models. Another representation bias, the figure on the top left, is geographical distribution of open images data set. This is one of the very famous image data set used in the world. And then the darker the shade, that's where the image comes from. Here, we have a few from India, lots and lots from America, a few from Australia, almost none from Africa and South America. I don't know. I think Nepal is also pretty white. If you zoom in, you can see. So again, right, and I'm sure I've used it in my projects. I don't know if you have. It's the same thing with ImageNet. Parts of Asia and especially South Asia are very, very poorly represented. So and then ImageNet forms the back end of most state-of-the-art computer vision algorithms. So any computer vision algorithms that we think of, that a lot of the times we consider like comparable to human accuracy, actually don't represent our part of the world at all. And that's a representation bias. And this kind of occurs because our data sets are unbalanced, but it's also easily fixable, right? It's easily fixable by just citing data. And the third one, this is kind of data set bias, kind of not, is what we call measurement bias. I love this comic. I hope everybody can read it. And this basically shows you the risk of designing a model, selecting a metric, and then not thinking about the consequences, right? use a data set, and then you use the data set and labeled people who are identified by dogs, because that's how we use it, as like people with drugs. And then what ended up happening is dogs are not a good measure of people with drugs. It turns out dogs like treats more than drugs. And so our model also learned to identify a doctor detector. That happens a lot. We learned about insurance this morning. A lot of features we use in insurance are similar. They are an inaccurate proxies of exactly what we want to measure, because a lot of the things we want to measure are not real or measurable. Same thing with disaster risk management that we heard about this morning. A lot of the things we want to predict or measure are things that are either going to happen in the future or things that are very, very rare, so we can't really measure it. So we think of the closest proxies, but in the process, we might be measuring something else. Again, the AI recruiting tool, because we use who was a good employee in the past as a measure of who is a good employee, right? So who got promoted was a measure of who is a good employee, which is only a proxy. That's a measurement bias. Another is criminals. This is a headline which I hope everybody has seen by now. It created lots of ripples. It's also used in every single bias presentation that I know of. But again, right, this was a software that was actually used in courts to predict future criminals. And it turns out, again, what they used was like past criminality and zip codes and income and all of that, which turns out in US is very much biased against Black people. And then once you flipped a few of those measures, the algorithm did not work at all. In terms of thinking about our own project, why does it matter? What should we think about is we should really think deeply about the features we use, the metrics we use, and try and consider whether what we are measuring is exactly what we're trying to measure, and what are the confounding variables, right, statistically. What's independent, what's dependent, and what's confounding variables, and try and isolate them and look at the impact. That's sort of how we can at least be aware, if nothing, because sometimes it's really difficult to measure exactly what we want to measure. And then also prevent this bias from seeping in, or let this bias seep in only in the cases we want it to. Another thing that I really like is what is called Goodhart's law, because a measure that becomes a target stops being a good measure, right? So again, think about algorithm, think about Google search. It was really good a few years ago. It's not as good anymore, and that's because a lot of people, right, a lot of advertisement have learned to game the system. Same thing with misinformation, right? And what happens is there's a perverse incentives. People who want to scam, people who want to advertise, people who want to spread fake news have a lot more incentive to game the system than normal, regular people writing blogs, providing good information, sharing their information. So if the metric is not updated, if the metric has this information imbalance, it also ceases to be a good measure. And so tying back to what I said earlier, right? Again, context is key. We need to remember where this metric came from and if it's relevant to the changing context of the world. Yeah. Now we move to evaluation bias. I hope people can still see the pictures and the initial big picture and where evaluation bias comes from. Evaluation bias is here. This is one of the key biases that exists in most AI algorithms that are deployed in the world and are not as talked about. Again, you should have seen this image by now. This is the face detection algorithm. And when it was evaluated on the basis of gender and race, initially it was just evaluated on a single data set. All of them had above 90% accuracy and were deployed in the world. And then later, a group of researchers, Timnit Gebru and all, evaluated it on specific demographic information and then realized that the accuracy decreases when it's male versus female, and it also decreases when it's white people versus non-white people, and it decreases significantly when it's a female non-white person. And the cause was that the evaluation benchmark data set did not have enough non-white female persons, so the algorithm was not optimized for it at all. If you've developed any algorithm, we know we basically keep optimizing until our accuracy is a certain limit, right? Sometimes you tune hyperparameters, and a lot of the times what you're trying to do is optimize it against the metric you have. So if your test is not representative, if your evaluation metric is not representative, this is where bias is introduced. We will go into a lot more detail about debiasing this or thinking about ways to make this more fair in the second half of this presentation. But basically think about it as the error that gets introduced or bias that gets introduced from test data set, test metrics. And one of the ways we can find it existing in the world is most algorithms are benchmarked against these standard metrics and biases, right? And data sets, right? For computer vision, it's probably ImageNet. For NLP, there's again certain benchmarks that everybody who publishes has to compare against. So over time, the algorithm perform better on those data sets, but may not perform as well in the wild or in the world. And if you're developing algorithms for not just for research and for deployment, you should evaluate it against both the state-of-the-art benchmarks, but also in a representative sample of your users. Aggregation bias is another bias that comes from model building. And so this is slightly more complicated and depends on assumptions of independence, right? So aggregation bias arises, I'm just going to read it as it is, when a one-size-fit-all model is used for groups with different distributions. And basically, to think of it in layman's terms, in simple English, is we're assuming that mapping from inputs to labels is consistent, right? Like the model that represents the input to output is the same regardless of where it is built, who it includes, what the input features are, and what the output categories are, which may not always be true. For example, I have two examples. The first one is a medical example where many algorithms until a few years ago used the same detection model for entire population to detect strokes. And this doesn't even have to be AI, right? Even doctors, when they check for symptoms, they had the same checklist, but stroke symptoms are actually completely different for men and women. Women don't get chest pain, which is what we've learned to hear is like an assigned to identify stroke. Women apparently get like hot flashes. And so up until a few years ago, many women would get strokes, but not realize it until too late and they were dying. And so this is again, because we had the same checklist, we had the same information flow, some gender groups, right? But the model was different for two different genders. The impact was had to be only one gender group was impacted. Similarly, on AI, misinformation models used by many of the social media companies, even Google, is the same or only slightly different across different areas of the world. They don't have a lot of content moderators who know the local language, local context. And what that has resulted in is that misinformation actually spreads much faster in the global south, which has led to dire consequences in Myanmar, in India, in Pakistan, in Rwanda, and more. So again, this is kind of another example of AI being deployed globally without considering of like little differences, which has caused a lot of harm. And it doesn't have to be a big thing like genocide in Myanmar. It can be something as simple as a traffic light detection model or a traffic light detection model, which you can deploy in Nepal, without realizing that there are no traffic lights, sometimes traffic policemen can override traffic lights, and then if the model doesn't account for that, you might get tickets, or vice versa, or cause traffic jams. So again, local context and use cases are really important, and sometimes it's okay to have a simple model that works globally or on a larger scale. Sometimes it's not. Scale, surprise, is not always your friend. Smaller model can sometimes be better, and if it's not, that's one way for entering bias. Lastly, deployment bias. How many of you have heard of the Tay robot introduced by Microsoft? I think this was introduced in 2016. I see one hand at least. Only one. Yeah. So this robot was introduced by Microsoft as like a fun way of basically copying Taylor Swift and interacting with fans. It was trained with NLP models, state-of-the-art NLP models at the time. It was designed to be cute and sweet, and then they released it. It was also designed to learn actively. So it was learning as it was interacting with people on Twitter. And so this probably is like one of the first tweets on the top left, and then towards the end, she turned full racist, full murderous, full Nazi, right? She's like, I want to murder everybody should burn in hell. And one of the reasons it happened was that people, right, tend to distinguish between humans and robots. So if you know something is a robot, we try to break it. Multiple psychology research has shown that. I used to work with self-driving cars. Many people, when they learn that a car is self-driving, would just try and come in front of it to get hit. Because, or like I used to work in robotics lab, and there's this tendency where we anthropomorphize things, but we also treat it differently. And with robots, because of probably Terminator and Matrix, that's my guess, right? People try to break it. And so for T-tweets, the engineers designing it did not put a fail safe of people trying to turn it evil. And people who tried to turn it evil, once they discovered the catch, it was really fun. Similar to when I showed the poll earlier, it was more fun to type Robin and Nistel than actually type the answers, right? It's more fun. It's more fun to troll, especially if you're anonymous. So that happens a lot when you deploy things in the wild. Things to remember when you build chatbots. And then sometimes this is fun until it triggers somebody, right? It could tell a suicidal person to go kill themselves, which is not okay. And so there can be really harmful consequences even when you don't think about it. So another question. Now that we know different sources of biases, what can we think? What can we do about it? Let's go. Back in the same Slido. I will share my screen soon. Okay, go. No bias, stop using AI, accept it. Robin. I'm gonna call on Robin to give an answer if he gets enough votes. Oh, oops. I thought this worked. Sorry about that. There you go. Human intervention, international rules, diverse data set. No more Robin. We need an AI to detect Robin and block it. Add some positive bias. If you want, you can also type it in Zoom or raise your hands and talk if you want to write longer than what it allows. I think we're okay on time. Train again, representation in data set, evaluation metrics, equality, more names, don't make Altron. Robin, you want to give an answer? Okay, let's go back. We're getting too many Robins now. So I don't know the answer here either. It is just a food for thought. I don't know what we can do about it. Maybe Robin does. But it's something I think we all have to be aware about and think about the impacts and the risks intentionally. So from there, we're gonna move to fairness, which is more complicated than removing bias. But if before I do, are there any questions? For biases, sources of biases, things I might have gone too fast, too slow, too repetitive. Anybody? Audience? Zoom? Going once? Going twice? Okay. Either I'm too clear or everybody's asleep. Okay, so moving on. This time I have another poll. How do I do this? Yeah. Back to the Slido. Yeah. So I have a poll. No Robin this time. So I have like a couple of examples of algorithms, and which one of these would you call a fair algorithm? And I think you can only vote one. So go. You guys can see the question, right? Nope. Huh. Let me try again. Yes. Okay, how many? 13. We have a few more people here. Let's go. Okay, let's give it one more minute. Huh. 54. Pretty divided, right? So some people think an algorithm that ignores features that have historically caused discrimination is fair. Other people think explainable algorithm is fair. Other people think algorithm that has the same outcome across all demographic groups is fair. No, not a lot of people think algorithm which can be predicted is fair. I feel like these two are kind of related though, explainable and predicted. So this is interesting. Yeah, I think now we have a winner. Slightly, but we have a winner. Right? Algorithm that ignores features that have historically caused discrimination. My question, and I would love it if somebody raises their hands and answers it, is how do you separate this from what we were calling representation bias earlier, right? Where the data set didn't think about these features that have historically caused discrimination. Anybody? No? Okay, let's go into fairness. It turns out fair algorithm is actually, it's a good thing that our room was so divided, because defining a fair algorithm is actually quite difficult. The first debate is individual versus group fairness. And in the slide, I have a picture of distribution of heights among men and women in the US. Median female, 5 feet 4 inch. Median male, 5 feet 9 inch, which is quite a lot when you think of heights, right? But at the same time, a vast majority of them are within this giant area of overlap, right? So there's few female who are on the shorter side, few male who are on the taller side, but a vast majority are around the same. So when there's a group difference, and gender comes to mind first because it's easier to think about, until like we go deep. Let's not go deep, right? Then it's easy to think of characteristics that have a group difference, right? For gender, it's easy to say nobody would disagree when we say like women are on the whole smaller, shorter, skinnier versus men. The chart shows that as well, but at the same time, large number of individuals share characteristics. So if you give a single data point of height, it's really hard to distinguish between whether that is a woman's height or a man's height. If you give a bunch of data points, then you can cluster them. But a single data point, it's really hard. And so when we think of models being optimized for different groups, right, defining a model for a man versus a woman, which a lot of these public product-oriented algorithms do, especially for advertisement, they can be either optimized for groups or individuals, and what is optimal, what is fair depends on context, but there's a trade-off. You will either be choosing fairness for group or fairness for individual. Yeah. So what is defined as group fairness is do outcomes systematically differ between demographic groups? So again, we've seen this example before. In both of these examples, right, the outcome demographically biased against specific demographic groups, women in the first one, Black people in the second one, and this is against the group fairness. But the debate is what happens if the prevalence of the thing that we're trying to measure, yeah. Mike? Okay. So the question is, we're going into it. Great question. I can repeat the question, probably easier. Yeah, so there was a question from the audience on whether I was referring to unbiased as fairness, or how do we define fairness, right? Yeah, so in the next few slides, we will try to define fairness. I haven't said a definition yet. One definition that's used is group fairness that I'm showing here, where outcomes of an algorithm should not systematically differ between different demographic groups. So if, right, an algorithm is supposed to recruit individuals, they should recruit the same number of men versus women, or changing the gender on a resume should not cause a different outcome. Seems fair, I hope, right? Like if you have a resume and then there's a field called gender, and then you put a male versus female versus third gender, the outcome doesn't matter. That's one definition of fair. But the question is, as it says, right, the prevalence differs between groups. So for some things, for example, in the aggregation bias, we talked about stroke, right? The prevalence itself might differ between groups. In this example, machine bias or AI recruiting, some people might claim that women are less interested in AI. Historically, the data shows that there are fewer women even present, despite affirmative action, despite a lot of effort, there are fewer women working in AI. So some people may claim, and I'm not giving a judgment one way or other, right? Like, what if women are less interested in AI? And what if our model learns that? Then in that case, right, fair is model learning what is true, right? If women like to do, say, nursing versus AI, then the model shouldn't penalize women who like to do nursing because there are more of them there, and maybe penalize men who like to do AI because there's more of them there, right? So another definition of fair is if an individual, or if the prevalence, right, is different between demographic groups, then the model should take that into account and show that in prediction. Mathematically, what it turns out to be is this shows up differently in our metrics: false positive versus false negative versus true positive versus true negatives. So if statistically more women like nursing versus AI, then we'll have fewer false positives in nursing and more false positives in AI when we try to optimize for like equal number of men and women, right? So the way it works is that shows up different in metrics. The second thing is that things like interest, things like prevalence are really, really hard to measure. So that's why I gave an example of gender in AI, right? I work in AI. I am always annoyed by the fact that there are fewer women in AI. And one of the things I think is because our educational system, the opportunities we have, the level of mentors we have, there are fewer women. So people don't have as much exposure, as much interest, as much opportunities. So where do we draw the line between prevalence, right, versus like what is statistically true versus what is systematically, societally true? And what is the ideal outcome that we want to happen? Because for me personally, it would be great to have 50% men and 50% women in AI, but it's not fair for if like 50% women don't want to be in AI to force them to come to AI, right? So this debate exists because we don't know what's the prevalence. We can't measure prevalence, one. And then two, defining what the ideal outcome is, be it in terms of like these higher level societal goals or specific metrics as false positive, false negative, true positive rates, have different societal impact. And to go back to the question, this is why defining fairness is hard, right? What is fair in this case is very contextual. It also depends on your individual value system, your moral system, your philosophy, your social goals, your political goals right now. Now it's not connected. It's not simple as having a mathematical definition. Yeah, but legally and mathematically, people have different definition of fairness. We will go through a few. And the first one is called equal treatment. Give me a second because I think I have a typo. I have a typo. This should be equal treatment here. I'll correct it before I share the slides to you. But the equal treatment fairness definition says that protected and unprotected groups, and a lot of this comes from legal definitions, human rights definition, from a lot of legal research, because algorithmic fairness research has been driven by social outcomes and what algorithms may be illegal, basically. Right? So equal treatment comes from protected and unprotected groups. So in this case, demographic groups, right? Our every law has some sort of idea of protected demographic groups. In Nepal, gender, caste, religion are some of them. In the US, gender, caste, disability, religion, sexual orientation are some of them, right? Race. So what this says is the protected and unprotected groups should have equal true positive and false positive rate. So if we think of Y as a binary classifier model, A is a demographic attribute or a feature, right? And this doesn't just have to be demographic attribute. This could be any feature. Once you go back to building classifiers, this could be any feature in your classification set, right? Then whatever the outcome of Y, right? Whatever the true outcome is independent of what your predictor outcomes is independent of the demographic attribute, right? So predicting Y is 1, the probability of your model predicting Y is 1 versus for like a class A, when class A is 0, let's say this is gender, right? When gender is male versus gender is female is the same. And what Y equals Y here means is that actual true prediction is also independent. And so on a high level, this means your true positive and false positive rates are equal. On a mathematical level, if you want to write it as an equation, it comes as like conditional probabilities of your model. The problem though is because we can't actually measure this true outcome, right? Getting this condition is really hard. We don't know what the true outcome is, so we can't really satisfy this criteria. So one way to kind of loosen it a little bit is what's called an equal opportunity fairness. So this is the second fairness definition, where now instead of having both equal true positive and false positive, we focus on true positive, which means nobody should be discriminated in terms of opportunities, right? So in hiring, there should be equal true positives for both men and women. Only men shouldn't be hired or only women shouldn't be hired, but we don't care as much about rejections. Like if there are lower female applicants, then fewer females can be rejected, but the proportion of men and women being accepted should be the same, true positives. And mathematically, this is how you write. The difference between the two is now we only care about when the true outcome is true, right? So Y equals to 1 instead of any value of Y. And then if you have multiple classifier instead of a binary classifier, this set would change. If you had multiple features, then your conditional would have more equations. But this is the way you would do it, and the way you would put it in code, which I didn't get into here because of time, is this would be a constraint in your optimization. So when you run your ARA optimizer or gradient methods, right, this would be one of the constraints. So you would only do the gradient step underneath when this constraint is satisfied. And that is how you would train your weights. Third fairness definition, and this more, is in this case, you don't care true positives or false positives. You just care that the outcome is independent of demographic attributes. So a person, what we said initially, right? Putting a male or a female in your resume shouldn't matter. That feature is just ignored. And this is the easiest way to implement, where you just ignore the features. This is also in practical use cases turns out to be more problematic and unfair, because these features can be encoded by other features, right? So whether you are a male or a female can come from your height, weight, as we talked about. Your race, your poverty level can come from your address, your social connections. So you can say you'll ignore the feature, but it's really hard to ignore all the features that represent a demographic attribute. And so, and also one of the way you do this is by going blind, but going blind, you may encode a lot of hidden biases, including representation biases. So this is a definition. It's the easiest fairness definition to implement. It is also the hardest fairness implement to actually make an algorithm fair. And if you are really interested in fairness, Mahendraji. There's many other definitions. This is a famous tutorial and a book. And these are all the lists. I'm not going to go through all of them. But if you are interested in fair algorithms, the math behind it, the way you would model different things, some of them you can test after the fact. Some of them you'd put it as a constraint in your training step or in your data gathering step. And these are some that people have used to develop different kinds of algorithm. There are more. Every day there's a new paper with a new fairness criteria. So area of active research, if you're interested to think about and get your brain a model a bit, lots of opportunity here. You have to be really good at stats. That's I think one way to think about it is like statistics. This is where you need statistics. Yeah. Any questions? Did anybody understand fairness? Did I confuse you more? Yes, no? Fire group, is everybody asleep? Yeah. Then, I hope you're not too confused, but let's dig a little bit into why does this matter, right? A question I get a lot is, aren't humans also biased? And if it's so difficult to define a fair algorithm, if people even disagree what like fair algorithm means, maybe we should give up. Some of the people had said that in Slido as well, right? Maybe we should give up. There's no hope. So why does this matter? Why are we talking about this? So one, and we saw this example in the morning as well, right? Machine learning can amplify bias. Gender bias from English is actually transmitted to languages without a notion of gender. We see that in our daily life as well, where like a lot of Christian groups in Nepal still have caste system, right? Which is a Hindu concept. And the way cultural biases, negative things transmit exists, machine learning can amplify it. There's a question. Can you pass the mic?
So I know like there's a lot of bias and all that, but is this like a fair example? Because what other way would you present it? Because you said it's a gender neutral language. So I mean, there's no other way of putting anything in there that would convey to Google that you're talking about a female. So it would just go with the statistically more accurate prediction of females being more nurses and doctors being more males.
I mean, that's one way to do it, right? But have you sent an email to an unknown person where you don't know the gender?
No, but this is gender neutral item. So I'm just asking, like,
yes,
how would you, what else would you do there?
So from English to Hungarian, right? It's fine. From Hungarian to English, the question is, right? So I'm saying when somebody sends me an email, right? Sometimes they send dear sir, which is very offensive. Sometimes they send you dear sir, madam, which I think is a better way to do it. Sometimes there's a sense to whom it may concern, right? All three of them are valid ways of sending emails. The first one is gender bias, right? They're just assuming because I'm a researcher, I work in AI, I'm male, which is what's happening here. The second one is, I think, clunky but accurate, a dear sir, madam. So in this case, it would be he, she is a nurse, he, she is a doctor.
Got it.
But that's a judgment call. Again, right? There's another way to whom it may concern. So there could also be a note at the bottom saying the gender is guessed and not predetermined. Again, here Google is actually making a judgment and then hiding it behind its algorithm without mentioning it, which is what I mean by amplify bias. Because over time, right, not many people speak Hungarian and a lot of people use Google Translate. So over time, what might happen is a language which doesn't have a notion of gender will get that built. So that's more problematic than just using the statistical method, because here Google is making a judgment call but not mentioning it, and that's I think is a bigger problem than just using the statistical model. Which leads me to my next slide. With great power comes great responsibility. It turns out that this notion of human being biased is kind of inbuilt into us, right? So if you go to a government office, somebody is biased against you, somebody is sexist, racist in like offices, in day-to-day interactions, in home, in schools, right? You kind of realize it, you don't internalize it as much, but we have this notion of algorithms being fair. We also have a lot of hype around algorithms replacing humans because they are more fair, right? So algorithms tend to be survey over survey over survey has shown that algorithms are trusted more than humans. And then the bottom example, it is a little funny. I'm sure it's slightly out of context, but 3 tourists ended up driving themselves into an ocean because Google Maps said so, right? This is like an extreme example of algorithms being more trusted, but many of us, including me, have driven into places like really narrow alleyways, which is one way or no way out because Google Maps told us to go there. And then you look at the road, you're like, I don't know if this road, like my taxi will go in, but the map says so, and then we go and we get stuck. So we've started trusting maps more, right? We've also started modifying our behavior a little more. Many of you probably use Siri. Many of you probably use Google Voice, Alexa, I don't know. And I'm sure like we've changed our accent so that it understands us better, right? We do modify our behaviors in small, tiny ways to make algorithms work to our benefits. And a lot of the times it again causes this power imbalance, right? Because algorithms are doing what, as he said, is statistically more likely. So people who are not in that median, right, the top of the Gaussian curve, are more and more disadvantaged. For me personally, as a female, I face that a lot along gender lines, or as like a smaller than normal human being along size lines, right? But we've all faced that in along one axis or other, especially being in Nepal, definitely along like regional lines, right? Not many features are optimized for Nepali context. And this again, um, being global, being scalable, being large scale will only get worse. And using data set from all over the world will only get worse if we're not aware. And so one way to fight it is being responsible, being aware, knowing it's a choice, right? This example, knowing putting Cis and he's a doctor is a choice, and in language, there's many other ways of doing it. Another way of doing it is putting they, he, she, right? We don't know the gender is undetermined. And so that's sort of where all this discussion about fairness, bias, the things you've been listening since the morning comes into play, is that if we don't know about it, if we don't think about it, we actually end up encoding what exists in society historically, structurally, powerfully, and then also amplify it to normal people, decision makers, public, where algorithms are trusted more. And so we end up changing human behavior. The last one, and I think somebody asked this question before, right? And he asked me about fairness. So what is debiasing an algorithm? I say it's impossible. There's no such thing as an objective algorithm. There's no such thing as a completely fair algorithm. As Kathy O'Neill, and I really like this book, highly recommended, Weapons of Math Destruction, algorithms are opinions embedded in code. So by choosing a set of inputs, which need to lead to desired outputs, we are creating an opinion, right? In a way, a bias. So by virtue of designing an algorithm, designing a model, putting a model in place which takes certain set of inputs, no model takes all inputs possible. And no model gives all outputs possible, right? We have to reduce the input space and output space to make anything viable. We are putting some sort of bias, some sort of opinions in there. Doesn't mean it's bad, but we are doing it. So moving on, we'll connect bias and fairness and ethics, right? And again, this is one way of thinking about it. Ethics is more complicated than one person's opinion. So take this with a grain of salt. You don't have to agree with everything I say. But the way I think about bias is along intentional and unintentional, right? Intentional bias are usually good to have. Unintentional bias when they're ethical. And then unintentional biases we should avoid, right? It's always good to know what the biases that go into an algorithm are. And so the way this table, and here's a source, frames it is what we want is biases that lead to desired outcomes, right? So maybe biasing an algorithm towards select hiring more women is good if our goal is to increase the number of women in AI. Our goal doesn't need to have that, but if we have that as a goal, then maybe we should bias algorithms to hire more women, right? If our goal is to reduce poverty, right? If our goal, say you're building an AI for development, your goal is to reduce poverty, then it's okay to bias algorithms which give more money to poorer people than richer people, right? Your algorithm should be biased towards the goal you have. For self-driving cars, it is okay to have an algorithm that is biased towards not hitting pedestrians, right? And when I design self-driving car algorithm, I would bias the algorithm to hit a pole, a curve versus hitting a person, because that's a goal. That's a good bias to have, right? But these biases need to be built intentionally with awareness, because otherwise you may think a person is a pole and go hit them, which would be unethical and bad, right? And then sometimes there is a trade-off between profit and ethics and use cases. And so knowing these biases will also help us make intentional decisions. And because without knowing, we may prioritize profit, which again, a lot of scandals around Facebook, right? A lot of the times these things were not known. So the bias, the only metric they had was profit metric. What increases engagement, what increases advertisement revenue, and then all the other considerations fell down the wayside. Without putting any blame, it's most likely from like unintended biases, but that's on this column, right? Not this column. And so towards ethical and unethical, and hopefully nobody in this class wants to be here where you know there's a bias, you know intentionally introduce it so that you can make a gain, because that's also possible, but that's completely unethical, and we're going to assume nobody will do this. It's probably also illegal. So what next? Should we give up on machine learning and algorithms? This bias, it's hard to remove. We can't even define fairness. Humans are also biased, but biased machine learning might be worse. So should we give up? Is the Sunday not worth it? Did you guys just waste your time? Hopefully not. So one way to think about it, and the way I like to think about it in my research and in my development work, is move from bias to harms, right? So beyond bias to harms, it's a talk. I have a list of resources at the end. So one way of thinking about harms is harm of allocation. So remember we talked about equal opportunity for fairness. Similar to that, right? Harm of allocation is when opportunities are removed due to algorithm because of biases. So this example we've been seeing, Amazon not hiring women. Another example recently we've seen a lot is algorithms around this gig work. So Pathao, Tutal, Uber, food delivery, right? Optimize for customer service because they are the people paying. They optimize for getting food, rights, whatever is delivered to people on time. And in the process, the workers who deliver it kind of have to run through bad weather, go through bad traffic, don't get paid for waiting time, right? Again, because a lot of this is done by algorithms automatically, they don't have anybody to complain around. And so this is a harm of allocation because we're prioritizing customers versus the workers, which in capitalism you do. And then because there's no way to complain, nobody looking for the benefits of the workers, they're constantly being harmed. Another harm is harm of representation. Again, an example we've heard many times, right? Google mistagged photos of African Americans as gorilla. Facial recognition technology didn't work for brown people, black people, Asian people. And then another example, the positive example, is when we did Google image search for CEOs. Again, statistical distribution, but most pictures were of white men, right? And then harm of representation is when an AI system does not work as well for one group of people as it does for another. This is directly related to representation bias that we talked earlier, but also to evaluation bias and deployment bias, where we develop it in one kind of setting and launch it in another. More cartoon. I really like this cartoon to distinguish between two different kinds of harms. For both of them, if you apply for a loan, harms of allocation is if you get rejected because of your characteristics, right? Here it's because your hair. Because your hair is weird, you don't get a loan. That's a bias against, say, curly hair, right? Against curly hair people. That's a harm of allocation. A harm of representation is when the algorithm does not even recognize you exist, right? Maybe the data set didn't have any curly hair people, so when you went there, it thought you had a statue. So that's a harm of representation. So how do we do that? Is valuing data in context. So again, a lot of the things I've said, there's no right answer. It really depends on your AI application, your AI model, your data, your use case, your goals, right? And so all of that can be lumped into what we call context. One way to model context in data sets is the seminal paper by Timothy Kebru and team, which is called Data Sheets for Data Sets. This is an example, but what they do is create motivation for, like, create a document. If you are from electronics and communications, you read some data sheets for resistors, wires, batteries, right? Similar idea. For civil engineering, we have these maps, building architectures, right? We use, in a lot of engineering projects, we do document things like specifications, product goals, failure modes, etc. But we don't do that a lot in software. So this is one way of doing that for AI, and specifically with data sets. You document where the data comes from, what the data contains, who collected it, how long should it be valid for, what use cases it should be used for. They have a couple of templates, but it's also really customizable to your use case. And then you can do the same thing for models, right? Google actually has a really nice tool called Model Cards. Check it out. Again, a way of documenting your system for who developed it, why did you develop, what is it valid for, when is it not valid, when it might fail, so that when you're using it or when somebody else is using it, they know exactly what they're getting into. If you're selling it, ideally, this is what you should sell it with, right? It's like a brochure you get with every single product. But in software, we don't get that oftentimes. So this is one way of like bringing other standards of engineering into AI development. Just for references. And then lastly, here are some of the questions that I like to ask during development. Again, a lot of these questions are contextual. Context, that's the keyword, right? But also some of these things, right? One definitely question that we should all ask is data-driven ML better than rule-based approaches? If you're working in safety critical applications. In driving, a lot of the times we had ML-driven applications, but a rule-based approach is like a backup, so that you could evaluate it against it. You could have it as a backup if the system failed, etc. Another thing is to be careful about is how do we determine what went wrong, right? Any engineering system will fail. It will fail at some point in its life cycle. And so as engineers, as designers, as product developers, we need to be aware and ready to go and do sanity checks, system checks, right? How do we determine when things went wrong? and how do we fix it? And then that translates into our evaluation metrics, that translates into our data sets, that translates into the team that is working on it, etc., etc. With that, this is all I have. I don't know how I'm doing on time. And then here's a lot of resources. It's an area of active research in both computer science and social science research groups, also statistics, human-computer interaction, AI, policy, law. If you look into university in the US, pretty much every single department nowadays have something related to AI ethics going on. So lots of research areas, depending on the level of math you want to be involved in. Feel free to ask me questions about that as well. Yeah. Questions, comments, reflections, too much AI bias. So I have a question on Zoom. Pariksit asks, would it be a good idea to build multiple niche models, each trained on a completely biased data set and construct an ensemble? Possibly. It really depends on your use case, Pariksit. Sometimes completely biased, if you know what the bias is, you might be able to overcome it. Sometimes you may not. Also, saying what is a completely biased model is hard to define, right? So sometimes it's better to have multiple models which work independently. Sometimes it's good to have an ensemble. It really depends. No good answer. Any other questions? Audience, Zoom? Ready for your break? There's one in the back.
Hello. I think more of a reflection than a question. One thing that's been missing in the last 11 days. Hello. Is the question of human in the loop. You mentioned that an AI algorithm knows when it's not really confident in edge cases. And one thing we've missed, I think even in today's presentation, is humans exist. We still exist, and we can correct correct the AI, or we can have systems where the AI needs approval from a human during those edge cases when it sees racial bias or in those edge conditions. And yeah, I think we can be too dependent on algorithms, and we can easily go into an engineer mindset where we optimize for variance and bias and all of these things, and those two graphs looks really nice, and we forget that humans actually exist. I'll tell you one example in my company. So we do transcription where we start with an AI transcript and then we correct it, and we started getting transcript of Black people, and then the AI transcripts were bad for Black people, right? And now our transcribers started asking a surge in the money we would pay them for. Hello. Yeah.
Do you want to come into the front and tell
Hello?
your story?
Hello. Okay.
No AI there, still biased.
Hello. Can you hear me now?
Yeah.
Okay. Why does so there was this important question of if we don't take those audios, then there's this systematic bias of we getting more data of people who have an American accent versus more other accents. And the way we did that was we did not put an automatic surge, we had a process where the transcriber would have to request a surge. A human would listen to the audio just a minute or 30 seconds and they would decide, right? So I think the question of human in the loop, because again, AI does not need to totally replace humans. I think AI is there to augment our capabilities. So that discussion needs also some space in this conversation.
Definitely. Thank you. That was not my intention. So thanks for bringing it, Puneet. Yes, and I think that's a great point. AI should not replace humans. Some of the questions I have here, right? I hope kind of indicate where humans can come in. One of them is answering potential harms, biases. Each of the bias stuff that I showed in the picture, right, can't really be answered by math. That's a human's job. Same with fairness, same with algorithm, and then some of these questions that I've highlighted here. How do we determine what went wrong? How do we determine our evaluation metrics? Who's in the team? That's all the places for humans to come in the loop. The other thing, and I think your example gives a great way, right? Sometimes it's better to have humans listen in and provide a way to incentivize certain outcomes than have algorithms there. And I think your example serves a very good example against the gig work headline that I showed, where having humans listen in and provide examples gives this added incentive to the transcribers to transcribe the data, which improves the data quality, but at the same time, it cannot be gamed. So yes, thank you so much for that example and reflection. Mike?
Hello. Yeah. So I have a two question. The first one is, since there are 21 definition of the fairness and maybe it is increasing, so do you agree on all of those definitions?
I think it's very contextual. Fairness, right? Let's try and go back if I can. Yeah, right. So some of these things are actually against each other, right? Demographic parity, or we had a brief discussion about individual versus group fairness. So dividing people into groups or buckets, right? Be it gender, race, location, might itself infringe on individual fairness, because if we group all Nepalis as one group, then Nepalis with like whose first language is Nepali versus whose first language is English versus whose first language is Hindi or Newari or etc. Right? They are all different people, and putting them in group and having a model which works well for Nepali is good for group fairness, but may not be for individual. Similarly, there is conflict between different fairness. What I would say is each of these fairness have their own use cases and are valid for certain societal outcomes, right? There's math behind it, there's ways to implement it, and then there's also higher level principle, value system, societal outcome that each of them are, for lack of better word, biased towards, right? And so and connecting to what Puneet said earlier, right? It's a job of a human to decide which of the fairness algorithm works best for the given use case. Second thing that I would say is algorithms are not set in stone, right? The world is changing, our data is changing, the way we use these algorithms might be changing. Like you might release it for a certain use case today, and then learn that your customers use it completely differently. In that case, you might have to optimize it for a different definition of fairness or a different metric, right? Or a different data set. So the other thing that comes into this ideas of bias and fairness is this concept of time, because humans are not static and the world is not static. It's changing, the context is changing, the definition of fairness and the use cases we are using is also changing. And some of these definitions capture that, some of them don't. If you're interested, I would recommend, I have linked, let's go back, 2 minutes slides. 21 definition of fairness and their politics. This is a tutorial by Dr. Arvind Narayanan from Princeton University. This is where I got some of those definitions from. So it's, I think, about 2-hour long tutorial. So go check it out.
Okay, thank you. So I have another question. Since like there are the other like physical model or the computational model that were existed before the field of ML or DL. So do you think that the concept of the fairness or biased are studied on those model too, or they are totally unbiased or fair?
Nothing is totally unbiased, right? And the idea of studying fairness is actually pretty old. There's been papers and writings that people have cited from 13th, 14th century philosophers as well. I don't know if you remember the talk from Connor, but he showed some of those older definitions as well. So this is not new. What is new and what AI ML has done is two things. One is it's completely data driven. So a lot of the things that people would intentionally put into equations and models and assumptions, right? Like if you come from physics background, a lot of it is approximation, or even engineering, right? We go down to these first principles and we're like, let's ignore friction, or let's ignore velocity, acceleration, right? So we've been doing this since forever, but nowadays, because it's data driven, a lot of those assumptions get masked. And so that's one problem with AI. The second problem with AI that we see in recent world is that it's globally deployed. So a lot of AI is being built by Googles and Facebooks and Apples. And then once it's developed, everybody in the world gets exposed to it at the same time. So the impact and the amplification that happens, right, is mind-boggling. That didn't used to exist before. And then the second thing is what it also does is because the world is so connected, the context collapse is happening at a much larger scale. So context disappears. A lot of the Facebook algorithms, people who develop it, right, may not even know of existence of Nepal. I have been told, right, when I say I'm from Nepal, is it Naples, Italy? So like a lot of people who work in Silicon Valley who develop these algorithms may not even know of existence of Nepal. So that kind of context collapse is another thing that today's large scale data driven models do, which didn't exist in the past. But in a smaller scale, this problem has always existed. Anybody else? I'm gonna stop sharing. I think we are out of time as well. So thanks for listening. And then I'm on Discord. I think most of you have my email, my NAAMII email. So if you have other questions, feel free to reach out. I love talking about this forever, so I can go on. But thank you so much for listening.